All right, welcome back to Talk Tensors. We are thrilled to have you join us as we, as always, dive deep into the fascinating world of machine learning research, particularly in this case, the super interesting area of federated learning, and more specifically, personalized federated learning, or PFL, as I'm sure many of you know it.
That's right.
And it's an area that has really gained a lot of traction in recent years, and for good reason.
Absolutely.
So, if you're involved in any way in building distributed AI systems, especially ones that deal with sensitive data like healthcare or finance,
right,
you've probably encountered the challenges of training models when your data is spread across a huge number of different devices or users.
Yeah.
And each of those data sets might have its own quirks, its own unique characteristics that make it difficult to train a single global model that performs equally well for everyone.
Exactly. You've kind of hit the nail on the head there. It's like trying to fit everyone into the same size shoe. It's just not going to be comfortable for anyone.
Right.
And that's exactly where personalized federated learning comes in.
Yeah. It's all about recognizing and embracing those differences, finding ways to create models that are tailored to the specific needs and characteristics of each individual client or device, while still maintaining that all-important element of data privacy that federated learning offers.
That's a great way to put it. So in this deep dive, we're going to unpack a really fascinating paper that proposes a novel approach to PFL. And what makes this paper particularly interesting for our listeners is that it goes beyond simply personalizing the final model for each client. It actually tries to learn and adapt the way those individual models are combined, the way they collaborate during the entire training process.
It's really quite ingenious.
And they achieve this by using a graph attention network to kind of figure out which clients have learned something that might be especially relevant to other clients, even if their data sets look completely different on the surface.
Yeah, and the paper is titled Personalized Federated Learning via Learning Dynamic Graphs.
Okay, so before we get into the nitty-gritty details of their proposed algorithm,
let's just take a step back and really articulate the core problem that they're trying to solve.
Right.
And I think it's important for our listeners to understand this because it really sets the stage for why this research is so impactful.
Absolutely.
So, as the authors point out in the paper, personalized federated learning, PFL, is all about training individualized models, specifically tailored to each client, especially when their data distributions are non-identical or non-IID, which is basically the norm in the real world.
Right.
Now, this is a significant departure from traditional federated learning, where the goal is to create a single global model that's supposed to work well for everyone. And as you can imagine, that approach can fall short when you have highly heterogeneous data.
Yeah, because what happens is that single global model ends up being a kind of jack of all trades, master of none.
Right.
It's kind of like trying to average out the preferences of a group of people who have vastly different tastes in music.
Yeah.
You end up with a playlist that no one really enjoys.
Exactly. And the paper goes on to highlight another crucial point, which is, if each client tried to train a model completely on their own in isolation using only their limited local data, they'd likely run into the problem of overfitting.
Yeah, exactly.
The model would become too specialized to the quirks of their specific data set and might not generalize well to unseen data.
Right.
So collaboration is key.
Absolutely.
But then the question becomes, how do you collaborate effectively when everyone's data looks so different?
Right. So that's the real challenge here. How do you strike that balance between personalization and collaboration?
Yeah, and that's precisely where their proposed PFED-GAT algorithm comes in.
Exactly.
And I have to say, the way they approach this is really clever, and I think it has some pretty profound implications for the future of distributed machine learning in general.
Oh, sure.
So let's walk through the algorithm step by step, and maybe you can help our listeners visualize what's going on here.
Absolutely. Happy to.
Okay, so the first key ingredient in this algorithm is the way they represent each client. And they do this by constructing a graph.
Okay.
And in this graph, each client is a node.
Okay.
But here's the interesting part. Each node doesn't actually represent the raw data on that client's device. Instead, it represents a compressed numerical representation of the machine learning model that client has trained locally.
Yeah, so it's not the data itself, it's kind of a summary of what the model has learned from that data.
Yeah, exactly. So you can think of it as each device creating a sort of fingerprint of its local model.
That's a great analogy.
And they do this by taking all of the model's parameters, flattening them into a vector, and then normalizing them.
Right.
And initially, this graph starts with what's called a fully connected adjacency matrix, which basically means that at the beginning, the system assumes that every client could potentially be related to every other client.
Right. It's kind of like saying everyone's invited to the party to start with, and we'll figure out who actually gets along later.
Yeah. Right. Exactly. So there are no preconceived notions of similarity or who might be helpful to whom. It's a completely blank slate for the algorithm to work with.
Yeah, makes sense.
Okay, so now comes the really cool part, the attention mechanism. And they use the graph attention network, or GAT.
Yeah, one of my favorite architectures.
Mine too. And this GAT sits on the central server.
Yeah.
And its job is to take those model fingerprints that we talked about and project them into a higher level mathematical space.
Right, a space where the relationships between clients can be more easily discerned.
Exactly. And once they're in this space, the GAT calculates what are called attention scores between every single pair of clients.
Okay.
And these attention scores, they basically tell you how much one client's learned knowledge should influence the personalized model of another client.
So it's like a measure of relevance or importance.
Yeah, exactly. So for your personalized model, the GAT is figuring out how much weight to give to the learnings of each other client. And this is where it gets really different from just simple averaging.
Right. Because now the aggregation process is no longer this blind democratic process where everyone's model gets an equal vote.
Exactly. It's more like a weighted average where the weights are dynamically determined based on these learned relationships.
Right. And to make this even more robust, they use multiple independent attention heads, which is kind of like getting a second opinion or a third opinion or even more opinions.
That's a great way to think about it. It's like having a panel of experts, and each of them is providing their own perspective on who the most relevant collaborators are.
Exactly. And then the final weight that gets assigned to each client's model for the purpose of building every other client's personalized model is an average across all those different heads.
Okay.
And here's where it gets even more interesting. This is where the client feedback comes in.
Yeah, and I think this is a really crucial aspect of the algorithm because it makes the whole learning process much more data-driven.
Absolutely.
So once the server has used the GAT to generate these personalized models, they're sent back down to the individual clients.
Yeah. And each client then evaluates how well that personalized model performs on their own local test data that the model hasn't seen before, and they send back a single number to the server, which is the test loss.
So they're not sending their updated model parameters back to the server at this stage. They're just sending a report card, essentially, telling the server how good the personalized model it sent down performed.
Exactly. It's like they're saying, hey, here's how well your recommendations worked for me.
I see. Okay. And what's so great about this is that it's much more communication efficient, right?
Absolutely. Because instead of sending the entire model back and forth, they're just sending a single number.
Right.
And that number, that test loss, is the crucial feedback signal that drives the entire learning process.
Okay.
So the server then uses those performance scores from all the clients to update the internal parameters of the GAT itself.
So it's a closed loop. The GAT learns from the actual performance of the models it created.
Exactly. It's like a self-correcting system. And that allows the GAT to dynamically adapt its aggregation strategy over time as the models continue to learn.
That's a very elegant solution. So they've essentially created a system that learns how to learn from the data.
Yeah, it's kind of meta, isn't it?
Yeah, it is.
And speaking of learning, I think it's time we delve into how well this algorithm actually performs in practice.
Okay, so let's talk experiments.
All right, so to really put PFED-GAT through its paces, the authors tested it on 3 commonly used image datasets: Fashion Amnesist, CFAR10, and on CFAR 100.
Okay, so these are all pretty standard benchmarks in the computer vision world.
Exactly, and they tested it under a variety of challenging data distribution scenarios to really see how it handles the real-world complexities that we've been talking about.
Right, so they didn't just assume that the data was nicely balanced and identically distributed across all clients?
No, they made sure to test it under more realistic and often much messier conditions.
Yeah, so they looked at a completely balanced, identically distributed scenario, which is kind of the ideal case. And then they looked at what they call a pathological distribution, which is designed to simulate extreme heterogeneity, where the data is highly imbalanced across clients.
Right, and they also tested it under more nuanced scenarios where the data distribution varied continuously across clients using something called Dirichlet sampling. And by adjusting the parameters of this Dirichlet distribution, they could control the degree of heterogeneity, kind of like turning a knob to make the data more or less diverse.
Okay, so they really covered a broad spectrum of possibilities there.
Absolutely. And here's the kicker. They didn't just compare PFED-GAT against a couple of basic methods.
Yeah.
They actually pitted it against 12 other state-of-the-art federated learning techniques, including both traditional methods like Federated and FedProx,
Okay.
as well as other personalized federated learning methods, and some even more specialized techniques that try to cluster similar clients together or optimize the aggregation process in various ways.
Right, so this was a pretty comprehensive evaluation.
It was, and the results are, well, they're quite impressive.
So what did they find?
Well, the headline is that PFED-GAT consistently either outperformed or performed on par with the very best of the comparison methods, and they saw this across all 3 data sets and across all the different data distribution challenges that they threw at it.
So it wasn't just good in one specific scenario.
No, it showed remarkable robustness across the board, which is really what you want to see in a practical system.
Right, because in the real world, you often don't know exactly what kind of data distribution you're going to encounter.
Absolutely. And they made another interesting observation, which is that some of the other techniques that they tested might perform really well in very specific, narrow settings,
Okay.
but then their performance would drop off significantly when the conditions changed even slightly.
So they were kind of brittle.
Yeah, exactly. Whereas PFED-GAT was much more adaptable, and often it achieved the best average performance across all the different conditions that they tested.
That's really compelling. And I think it speaks to the power of using a graph-based approach to model client relationships.
Absolutely. And it's not just PFED-GAT that showed this trend. They also found that another graph-based method called SFL also demonstrated good robustness.
So it seems like this is becoming a more and more promising direction for the field.
Yeah, I think so.
And did they look at how the method scales as the number of participating clients changes?
Yes, they did. And they found some really interesting trends there as well.
So what happens when you add more clients to the mix?
Well, initially, as you add more clients, performance tends to improve, which makes sense because the system is being exposed to a wider range of data patterns.
Right.
But then they observe that if you keep adding more and more clients, performance can actually start to decline.
So it's like there's a sweet spot.
Exactly. And they speculate that this might be because each client ends up with a smaller local data set,
Right.
which makes effective local training more challenging.
Yeah, that makes sense. So it highlights the need to strike a balance between the amount of data per client and the overall diversity of the data set.
Precisely. It's a trade-off that you have to carefully consider when designing a federated learning system.
Okay, now in the analysis section of the paper, they go a bit deeper into trying to understand why PFED-GAT works so well.
Right.
And one of the key questions they address is whether using a graph structure is truly beneficial for optimizing collaboration.
Yeah, because you can imagine just trying to directly optimize the weight allocation matrix without using a GAT.
Right.
So they actually tested that approach as well.
Yeah.
And the results were pretty clear. The GAT-based approach consistently outperformed the simpler method.
So the GAT is really bringing something to the table here.
Absolutely. And the authors attribute this advantage to the GAT's ability to explore a much richer, more complex space of possible relationships between clients.
All right.
And they do this through their nonlinear transformations and the use of multiple attention heads.
Right. So they can capture more nuanced and intricate connections than just a simple linear adjustment to a weight matrix.
Exactly. And they also provide some really insightful visualizations in the paper that help to illustrate this point.
Okay, so what do these visualizations show?
Well, they show the learned weight allocation matrices under both the balanced IID data distribution scenario and the highly imbalanced pathological scenario.
Okay, and what's the difference?
Well, in the IID case where the data is similar across all clients, PFED-GAT correctly learns to assign relatively uniform weights to all the clients.
So it's saying that everyone has something equally valuable to contribute.
Exactly. And interestingly, they note that some of the other methods they tested, like FedAMP and CFL, actually struggled to capture this uniformity.
Yeah, so they were kind of overfitting to the specific clients.
In a way, yes.
And what about the pathological case?
Well, in that case, where the data is very different across clients, The visualizations of PFED-GAT's learned weights show a much more differentiated pattern. It assigns much higher weights to clients that have similar data distributions and significantly lower weights to clients that have very different data.
So it's selectively amplifying the contributions of the most relevant clients.
Exactly. And this is really important because it prevents the negative transfer of knowledge, where you might actually harm your local model by incorporating information from clients that are working on completely different tasks.
Yeah, it's like getting bad advice from someone who doesn't understand your situation.
Precisely. And they point out that some of the other methods they tested sometimes missed these opportunities for targeted collaboration. They might overlook valuable, albeit less direct, information from seemingly dissimilar clients.
I see. So PFED-GAT is much more discerning in how it chooses its collaborators. And they also looked at how well the algorithm generalizes to new clients who might join the federated learning process after the initial training is done.
Yes, because that's a very practical concern.
Yeah, it's like what happens if a new user joins the platform.
Exactly. So they designed an experiment where new clients joined after a certain number of training rounds. And they found that PFED-GAT was much faster at adapting and identifying the most relevant collaborators for these new clients.
So it showed good generalization ability.
Exactly. And that's really important for real-world systems where the set of participating devices or users is constantly changing.
You don't want to have to retrain the entire system from scratch every time someone new joins.
Exactly. So this experiment really highlights the flexibility and robustness of PFED-GAT in dynamic environments.
So we've talked about the algorithm, we've talked about the experiments. But I think it's important for our listeners to understand the historical context of this work.
Absolutely, because this paper doesn't exist in a vacuum.
Yeah, it builds upon a rich history of research in federated learning and personalized federated learning.
So to really appreciate the significance of this contribution, we need to take a step back and look at the evolution of the field.
So how did we get here?
Well, federated learning really started gaining momentum around 2017 as this privacy-preserving paradigm for training machine learning models on decentralized data. And initially, the focus was largely on the fundamental mechanics of averaging model updates from different clients. But it soon became clear that this approach wasn't really cutting it when the data was highly heterogeneous.
The one-size-fits-all model doesn't always fit.
Exactly. And that's what led to the emergence of personalized federated learning, or PFL.
So when did PFL come on the scene?
Well, early efforts in PFL started appearing around 2018, 2019. And initially, a lot of the focus was on taking that globally aggregated model and then fine-tuning it locally on each client's data.
So it's like a two-step process. You train a general model and then personalize it.
Exactly. And methods like PFED-GAT are a good example of this approach. And there were also some early attempts to train completely separate personalized models for each client, often drawing inspiration from multitask learning. And methods like Onisha fall into that category.
So those were kind of the early days of PFL.
And back then, the aggregation process itself was still pretty much a fixed operation. It was just a simple averaging in most cases.
But then things started to change.
They did. And more recently, we've seen a real shift in the field towards trying to make that aggregation step much smarter and more adaptive.
And that's where methods like FedPer, FedAH, FedAM, CFL, and IFCA come in.
Exactly. These methods all represent attempts to introduce more nuanced control over how clients collaborate. Often based on some measure of similarity between their models or their data, or by trying to cluster similar clients together.
So they're trying to be more selective about who they learn from.
Precisely. And PFED-GAT builds directly upon this evolving landscape. By introducing the powerful machinery of graph structures and attention mechanisms, drawing inspiration from the success of graph neural networks.
Like GCNs and GATs.
Exactly. And it represents a real step towards a more dynamic, more fine-grained, and more data-driven approach to collaboration in federated learning.
So it's a natural progression of the field.
I think so. It's taking the best of what we've learned so far and pushing it even further.
So to summarize for our listeners, what are the key takeaways from this paper?
Well, I think the biggest takeaway is that PFED-GAT really demonstrates the power of dynamically learning client relationships. It shows that by using a graph structure and an attention mechanism, you can gain much finer control over how those individual models are combined, and you can achieve significantly better performance, especially when the data is highly heterogeneous.
And the end-to-end optimization using client feedback, that's another key innovation.
Absolutely, because it makes the whole process much more efficient, and it ensures that the aggregation strategy is constantly adapting to the actual performance of the models.
And those strong experimental results, I mean, they really speak for themselves.
Yeah, I think they provide pretty compelling evidence that this is a very promising approach for a wide range of real-world scenarios.
And I think it's important to emphasize the implications of this research for applications where data is inherently diverse and user privacy is paramount.
Right.
Like healthcare, for example, where you have patient data spread across different hospitals and institutions.
Yeah, or even in the realm of personalized education, where learning platforms could use this kind of approach to tailor content more effectively to each student.
Absolutely. So the potential impact of this research is really quite significant.
I agree.
All right, so now for our novel notions segment.
Okay, this is where we get to speculate a bit.
Yeah, so we're going to take the core ideas of this paper and try to extrapolate them, maybe think about some future research directions that could build upon this foundation.
Sounds fun.
So one thought that came to mind as I was reading this paper is, they're using a graph to represent the relationships between clients.
Yeah, right.
And they're allowing the edge weights of that graph to change dynamically based on the attention mechanism. But what if we went a step further and allow the graph structure itself to evolve over time?
So not just the weights, but the actual connections between clients.
Exactly. So you could imagine a scenario where if two clients consistently show really strong collaboration, their connection in the graph could become stronger, or even a new connection could form.
Yeah, like forging a new friendship.
And conversely, if two clients consistently show very weak collaboration, maybe their connection could weaken or even disappear entirely.
So it's like a dynamic social network of learning agents.
Yeah, and this could potentially involve incorporating meta-learning techniques to learn how to best adapt the graph topology over time.
Right. So the system would be learning how to learn the optimal graph structure.
Exactly. And this could have a really interesting impact on the speed of convergence.
Yeah, because it would allow the system to quickly focus on the most productive collaborations.
Right. And it could also enhance the system's ability to adapt to significant shifts in the data landscape, like the arrival of entirely new types of clients.
Yeah, imagine a new sensor being added to an IoT network. The graph could dynamically reconfigure itself to incorporate that new sensor and find its most relevant peers.
Exactly. And of course, this raises new research questions, like how to ensure the stability of the graph.
Right.
How to prevent it from changing too rapidly or erratically.
Yeah, but I think it's a really compelling direction to explore.
I agree. And here's another idea that's a bit more semantically oriented.
Okay.
So currently, PFED-GAT is learning relationships based on the similarity of the model parameters themselves.
Right.
But what if we could somehow inject some form of prior knowledge about the underlying tasks or data distributions of each client?
Okay, I see where you're going with this.
Yeah, so instead of just relying on the raw numerical fingerprints of the models, what if we could also incorporate information about the semantic similarity of the tasks that each client is trying to solve?
Right, so it's not just about how similar the models look, it's about what they're actually trying to achieve.
Exactly, and this could be particularly beneficial in scenarios where the model parameters alone might not capture the full picture.
Yeah, like if you have two different medical imaging devices, their initial model parameters might look quite different because of variations in the image acquisition process.
Right.
But if they're both trying to detect the same type of tumor, for example, there's a potential for valuable knowledge transfer there.
Right, even if their models look different on the surface.
Exactly. So the challenge is how to effectively and privately extract meaningful semantic representations of those diverse local data sets in a federated setting.
Yeah, that's a tricky one.
But if we could crack that nut, it could lead to even more informed and efficient collaboration.
I agree, and it kind of ties back to the idea of using graph embeddings, right?
Right. It does. It's like we're trying to create a richer representation of the clients that captures not just their numerical features, but also their semantic context.
Exactly. And that could really unlock a whole new level of understanding and collaboration in federated learning.
Yeah, I'm excited to see where this research leads in the future.
Me too.
Yeah.
All right. Well, that brings us to the end of our deep dive into personalized federated learning via learning dynamic graphs.
It's been a great discussion.
It has, and I think this paper really highlights the increasing sophistication of personalized federated learning techniques.
Yeah, and the importance of understanding and modeling the complex relationships that exist in distributed data.
Absolutely. So for our listeners who want to dive deeper into the technical details of this work,
Right.
the link to the research paper is available in the episode description.
And we highly encourage you to check it out.
And as always, thank you for joining us on this exploration of the cutting edge of machine learning research.
It's been a pleasure.
We'll see you next time on Talk Tensors.
Bye for now.